Good morning. I'm going to pick up where Mr. Davis left off. So let's take a look. I know you've seen this slide. This is where Mr. Davis ended last time, but I want to make sure we review this a little bit because this is a big deal. So let's say we wanted to study the Lewis and Clark population. Now, again, population, you'll see on the slide, population is the group of people we're studying. That is everybody in the group we're studying. Studying LC population, studying people in Spokane, doesn't matter. That's the group we're studying is the population. How do we get a random sample? What does a random sample even mean? Well, a random sample means that everybody in the population has an equal chance of being chosen for the study. So if I get a random sample of 2,000 students, that means every student at Lewis and Clark has an equal chance of being chosen for the study. So let's say we get our sample. Our sample is 50 students out of 2,000, and it's a sample. It's not the whole thing. It's a sample of 50 students. Then we're going to say we're going to test the effect of music on grades. Doesn't matter. Half is going to get music, half is going to get nothing, and we're going to compare the two. Now, how do we split those up? We have a random sample, and then we have to randomly assign them into two groups. That is random assignment. So each person in the sample has an equal opportunity to be assigned to the other two groups. So I wanted to make sure that you understood that. And then the placebo effect, I'm going to show a video on that. Maybe Mr. Davis will too, so we can explore that a little bit more. Okay, so what must a controlled test have? It must be blind. And what that means is, let's say, let's talk about a drug experiment. Drug experiments work really well for these types of things. So let's say we're testing to see if a drug is effective to treat anxiety. So we give, if we have, let's say we had that random sample we were just talking about, 50 students. We give half of the students 25 the drug, half of the students we don't give the drug. And in fact, what we would truly do in an experiment is we would give a third of the people the drug, a third of the people no drug, and a third of the people a placebo, a drug that seems like it might work, but it's usually just a sugar pill or a salt pill or something like that. We'll see if that works. But the whole point of that I'm trying to make here is they can't know which one gets the real drug and which one gets the fake drug. If you know, that ruins everything. So if it's a blind test, what that means is you don't know what you're getting. Obviously, you'd know that you're not getting a drug, but if you were getting a placebo or the real drug, you wouldn't know. It would be blind. The gold standard of experiments, though, is a double blind. And what a double blind means is not only do you not know what you're getting, I, as the experimenter, the person giving you the drug, don't know what you're getting. Now, how would you do that? I would have to know, right? No, what I would do is, so I would say to my assistant, I would say, give these people the drug. And my assistant might say, well, is this the drug or the placebo? And I'd say, that's not for you to know. So the person giving the drug to the person doesn't know that they're getting the drug or if they're getting a placebo. And the person getting it doesn't know. So nobody knows who's getting it except me. And I'm the experimenter and I've backed out of it. So a double blind study is really important in order to make sure that we don't kind of signify to people what they're actually getting. We want it to be completely scientific and everything the same except those drugs. And then we might have confounding variables. And when I think of confounding variables, now these are variables, we want to control variables. We want to make sure that everything's the same. If we're doing let's say we're doing the music and grades experiment that we were talking about just a second ago. Let's say we're doing it and we're testing it on a bunch of different classes. We tested on first period, fourth period, and sixth period. Now, we want to try to keep everything the same. We want the music to be the same. That's a controlled variable. We want people listen to it for 10 minutes and only 10 minutes. That's control. We want to control everything. But there are certain things that sometimes we can't control. For instance, the difference between first period and sixth period is different. That's a confounding variable. What that means is, are you better off? Are you paying better attention to first period or sixth period in a normal day? Not during the pandemic, but in a normal day. You're really tired in first period, right? So things are different in first than sixth. If we wanted to control that, then we would probably have everybody do the experiment at the same time. But because we can't, there might be a confounding variable. So confounding variables are the ones that we don't control or can't control. So we have to try to control every variable. Everybody gets the exact same experiment at the exact same time in the exact same way. And those things that are different are confounding variables that might end up screwing up our experiment. So we would have to be very, very careful. All right, we're going to do some practice on this later, so you're going to be okay. And then the dependent variable. So we gather data. Now notice I'm going to put up here, when we perform a controlled test, the independent variable is what I change as the experimenter. So I would say this person gets the drug, this person doesn't get the drug. That's the independent variable. It's independent because I can move it around, like it's totally independent. Now, my outcome, does the drug work better than the placebo? Do I know before the experiment whether it's going to work better than a placebo or not? No, I don't. Of course not. Because it depends. Aha, dependent variable. See that? So the dependent variable depends on what the outcome of the experiment is going to be. So I manipulate as an experimenter the independent variable, the drugs or the music, and then the dependent variable is my outcome. Am I going to find that it worked? Don't know. Hard to say. The only way we'll know is by doing the experiment. And then that's some practice we're going to do in class. And then we decide, is the hypothesis true or not? Did we validate that? Did it work? Or is it the null hypothesis? There's no effect. We just don't know. So we have to say. So then we look at it and we say, wow, people who listen to music had so much better grades. Or people who took this drug didn't have any greater effect than the people who took the placebo. Both of those are fine. We just need to know our result. We analyze it, and we're going to look at some statistical analyses coming up here in a bit, and then must withstand the scrutiny of the scientific community. One of my favorite examples of this was when I was in college. They did something called cold fusion in physics, which they've been trying to do forever. And that's like, cold fusion, great. This professors at Utah on the cover of Time magazine. Cold fusion is here. Our energy problems are solved. And then they published it, and my physics professor at the time at University of Washington said, I'm going to try to replicate this experiment, and he tried and it didn't work, and he called some people at other colleges. Did you try it? Yeah, I tried it and it didn't work either. So we publish so that other people can look at it, try it, and try to replicate it. And if they can replicate it, then it's like, yeah, awesome, we have a new finding. And what happened is they couldn't replicate. It wasn't that these guys were the guys who found the original finding were trying to be fraudulent or anything like that. They just screwed up. And that's why you publish. You publish and you say, hey, everybody, you try it. And if you screwed up, then we find out you screwed up. And if you didn't screw up, we go, wow, that's pretty cool. And then we know it's a scientifically valid finding. Okay. And then we're going to get to the experiment, which is what we've been talking about. We manipulate that independent variable. This is, if you want to prove something, if you want to prove cause and effect, you do a correlational study, right? No. Correlation does not prove causation. If we want to know cause, we have to do an experiment. I say, everything's equal. You take the drug, you don't take the drug. We're going to see which one works better. That is, the independent variable is the drug. The dependent variable is, did it have an effect? And then, as I said here, the researcher hopefully controls everything. We have all these controlled variables so that the confounding variables are kept to a complete limit. They manipulate the conditions. We have everybody in all groups, in both groups or in all three groups if we're doing a placebo, doing exactly the same thing. So we know that if there's a change, the only difference was what I manipulated, the independent variable. So any change can only be attributed to what I did. That is what we do for an experiment. And I'm going to leave off here and let Mr. Davis take over.